Vanakkam. Welcome to this course on biomedical instrumentation. We have been looking at pressure sensors, biomedical pressure sensors. In the previous video, we looked at classification of pressure sensors as intravascular and extravascular, direct and indirect, and what is the advantage and disadvantage of each of these, what are the applications of each of these, and we looked at some detail into some of these. In this video, we will look at intravascular pressure sensors, that is those that have a sensorized catheter tip that are really small, diameter of approximately 1.67 mm, one type of catheter, that have a sensor at the tip, have a working, and we will discuss the working principle, the types of sensors that are used and the applications, and what are the various catheter tip pressure sensors that are available. We looked at this in the previous video. These are sensors that are placed at the tip of the catheter, so there is no need for coupling with the fluid. So, it essentially eliminates the fluid filled catheter, which is the extravascular sensor. So, it directly senses. These provide high frequency response, so they are very fast, so can accommodate relatively rapid changes in pressure, can measure relatively rapid changes in pressure, and they are highly sensitive and they have high fidelity. They have very minimal delays when compared with the extravascular system. Why is the extravascular system going to have more time? Because the pressure wave will have to travel the entire liquid column. So, there is a delay, non-zero time, it takes non-zero time for this to happen. And what we measure is, we measure the displacement of the diaphragm. What are the various types of sensors that can be used for this? First is the strain gauge sensors. These are sensors that are bonded onto a flexible diaphragm at the catheter tip. So, that is, these are sensors that are attached, or essentially the catheter tip is sensorized with a strain gauge. What is the strain gauge? We discussed this previously in one of the previous weeks. If a metal foil, in this particular case we can discuss the case of the metal foil, if a metal foil is exerted, is exposed to a stress, it undergoes a strain, it essentially changes dimension geometrically, that will change its resistance. It turns out that we could measure the change in the voltage, and we could essentially relate the change in this voltage directly to the change in the resistance, and because the change in the resistance is directly related to the deflection that is causing this change. If all these relationships are linear, and all these relationships are linear in a range, we could relate the change in the voltage to a change in the pressure. So, these are quite common in FI catheters. Those that have 1.67 mm outer diameter. As technology is improving, smaller and smaller sizes are getting developed as technology keeps on improving. Fiber optic sensors, on the other hand, measure the pressure by detecting the reflection of light or the change in the reflection of light due to displacement of the diaphragm. This is safer in MRI environments because there are no metal parts, there are no parts of this sensor that are going to be affected by the MRI system. So, due to the lack of electrical components, because the system is purely optical. But the challenge is that this requires an additional lumen because we are interested in measuring relative pressure, and that is a disadvantage with fiber optic sensors when compared with strain gauge sensors. Now, let us look at the working principle of the catheter tip sensors. The first step is to insert a small diameter catheter that has an embedded sensor into the artery or vein of interest. First of all, this is a clinically sensitive procedure that only a few people, that only qualified medical professionals can do. And then the pressure is detected either using strain gauges. How does this work? As the blood is flowing, we already discussed this, essentially a manifestation of Newtonian mechanics. As the blood is flowing, as the fluid is applying the pressure, the material of the strain gauge essentially deforms, leading to a change in the resistance, and that change in the resistance is reflected as a change in the voltage. This is the working principle. We have discussed this working principle in one of the previous videos. Also, the pressure change in the optical case, the pressure change essentially changes the position of the diaphragm, thus changing the reflection characteristics of the light that is incident, and so the photo detector that is used detects the reflection characteristics or the changes in the reflection characteristics of this. These sensors convert this mechanical signal. What is the mechanical signal of interest? In this case, the mechanical signal of interest is the pressure into electrical or optical signals. The optical signal can further be converted into electrical signal for real time monitoring. The advantage and the applications are in cardiac catheterization, essentially used to measure pressures in the heart chambers. Also, if you are interested in measuring ICP values, intracranial pressure in head trauma or in neonates. Neonate means newborns. Or if you are interested in having MRI compatible pressure monitoring, because we may be interested in taking an MRI while the person is being monitored for pressure changes. There are such applications, there are such needs. Several clinical applications require very fast response and minimal drift, and high frequency, very fast response, high bandwidth and minimal drift. Current research in this field is focused on developing an array of sensors, several sensors that detect pressure, so that we could try and map to a true pressure value using multiple sensors. So, you can have a matrix of sensors, an array or matrix of sensors that is being used. What are the advantages? The advantage is that the pressure sensing element is placed at the tip of the catheter. So, there is a direct, accurate, high fidelity, high frequency, fast, rapid measurement of vascular pressure, in this case cardiovascular pressure waveforms. And there is no change, there is no time delay in the readings, because there is no fluid filled catheter. There is no time delay in readings since the sensor is right at the source. It essentially offers a flat frequency response. That is, flat frequency response means the gain or the attenuation remains constant over a relatively large range of frequencies. That is what is meant by a flat frequency response. That means it can detect changes that are either very fast or relatively slow without compromising on the accuracy or fidelity of this. So, essentially it is able to capture relatively fast changes, rapid pressure changes with high fidelity. Extravascular sensors usually have a need for continuous flushing of saline. It is fluid filled catheters require to be zeroed frequently, flushing of saline. This is a constant requirement in extravascular systems. In catheter tip systems, that is not a requirement, and it is not much affected by catheter movement, essentially providing more stable recordings. Now, what are the disadvantages? A major disadvantage is that it requires frequent recalibration. It requires to be recalibrated quite frequently. Also, these sensors are usually quite fragile and quite expensive, not exactly the inexpensive sensors. So, quite fragile and expensive, can be prone to biofouling, can be affected by the flow of blood, its performance can be affected. Another factor can be that there can be shear forces that the sensor will have to withstand and tolerate without getting damaged. That is the another factor that is often overlooked. There will be considerable amount of shear. So, the sensor is only measuring forces in a particular direction, but it may not be able to measure forces or pressure in directions that are parallel. So, if there is a shear force, it will not only not be measured, but it will also have a tendency to continuously and consistently erode or damage the sensor material, thus requiring relatively more frequent replacement, which is difficult because these sensors by definition are high fidelity, high accuracy, and hence more expensive. So, replacement is quite costly, especially in this case because it is directly exposed to the flowing fluid. There is a chance for shear to affect the performance of the sensor. With this, we come to the end of this video. In this video, we looked at intravascular pressure sensors, its working principles. What are the types of intravascular pressure sensors? We looked at two examples, strain gauges and optical systems, and the applications, and how we can catheterize these pressure sensors, and what are some of the advantages and disadvantages. What is a major disadvantage? A couple of disadvantages: shear forces it will have to withstand, and biofouling can affect its performance. These are some of the and it is more expensive and it requires more recalibration. The advantages are already very well known, I have mentioned many times. So, with this we come to the end of this video. Thank you for your attention.